registering. So first of all, with respect to the evaluation of the second part of the semester, which corresponds to partial 2, whatever this means to us, in the Blackboard, I have added assignments. Okay, so I'm going to share first my screen so that I can show you. Tac, tac, right, and then here. So I'm going to start with the lab because this is what I have here. So in evaluation and knowledge control, you will see that there's an HO2 data processing at scale that is worth 30%, so 30 points. You have already done a big bunch of the activities related to this block. You have already done something about the first steps towards MapReduce programs. Also to data processing and analytics. These are the two, the collective activities and other activities that we have been doing and that I have observed, and I have the input there. So these are the two ones, and the only one that we haven't still, and I haven't proposed the description of the activity, is first steps into data flow-based programming. This will happen during the weekend, and the idea is that it's not for the 9th of April. It will be due to the after the spring break. Okay, so that's for the lab. It will be very simple with respect to the to Spark. I will propose some exercises that you will have to program a little bit and to run on the platform that we have been acquainted to, and then after the spring break we will go to more cluster-like setting. But for this we will wrap up like this, and so there's only one activity missing, and that will be done with a lot of time still. So that's for for the lab, and then for the regular course. For the regular course. So partial 2, again, it's 25 points worth, and you have already done the execution in MapReduce programs on Hadoop environments. You already have done the programming data processing with MapReduce. You have already done the data processing with MapReduce. So these are all activities that we did together. There was Kahoot, there was other collective activities. So this is done, and the only thing that will be that is missing and that you have to do for, I mean, after the spring break, is the part of Spark that, as you can see, it's 5 points worth. So it will be again a short theory exercise in regarding the aspects that we have been studying and that we will complete between today and tomorrow with Spark. And with that, we will have partial evaluation 2. And then eventually we will have partial evaluation 3, which will be very simple because it will be configuring containers, etc. So that will be very simple, and so that you will not get overwhelmed with the last part of the whole of the semester that you have to address, not only for the course but for the other courses. Trying really to finish more or less when the classes will finish, we will finish. I will give some dates in order that you catch up eventually with activities that for which you will need more time. But the idea is that for the other courses, if you're having exams or projects or whatever, you will be free for doing this, and we will close the course very early in the week of exams so that you are free to do other things. Okay, so that was for the administration. If you have questions, please do. Yes.
Hello, teacher. Yes, I have a question regarding. So we don't have anything to deliver this Saturday, right?
No, it
Uh,
was intended to be this Saturday. Well, I mean, this Saturday. I'm not sure. Let's see.
yes, it was
Yeah,
the.
tomorrow.
Uh, um, this is the story of the 5 points, but I think that you have something missing over here, no, for this Saturday.
No, it was in the lab part.
In the lab, so let's go back to the lab, that I don't tell you lies. Because there was one of the exercises that I think that was due to this. Saturday 26, Wednesday 6th of April, so this is done. No,
Okay.
what did you have to do? It was this one, no? No, but descriptive statistics you have already done,
Yes.
and then yeah, it's only the
Only for Monday,
no,
right?
everything will be
We
for
return.
yes, yes, for the 18th, yes, right. Yeah, I might have. I was not sure when were vacations. So at some point, I might have announced some activity due to this weekend or to the week, but then I realized that there was spring break, so I postponed everything for after the break
The break. Okay. Yes, it was the. Just
because
that it's
spring break
Saturday.
is on Sunday, no?
Sorry. Uh,
Spring break is on Sunday.
just it starts on Sunday. Yes, just about an activity that is the two parts that we already done, where both it was we were supposed to also deliver one, but you pass it to Monday, so it's not for Saturday.
Yes, exactly.
Okay,
I postponed it. Yeah, that's right.
okay. And teacher, I don't know if it's
So
possible, but
yeah.
could we separate the lab and the theory course
And
delivery?
the date?
Yes, it's just that
Well,
yeah,
one is
are the
for
same
the
day.
18th, and I think that the other is for the 19th. Let me just have a look. The lab is for the 18th, and then oh, I see. Yes, I can say, well, we can say that the use case is for later, I mean, by Wednesday, for example, things like that. Even if I will try really to concatenate both, even if one is for the lab and one is for the regular course, but since everything is about Spark, you will see that there is, I mean, they're complementary. You can even do them together. But yes, of course, I can postpone the one for the regular course later on.
Okay, teacher, thank you. And I believe my teammates are asking something in the chat.
Yes, there are other questions, but in the chat. Wait a minute. Chat. Right now, we have activity for tomorrow. The HO2. Well, I will have a look, but anyway, it's not for tomorrow. Okay, I might have, since I have to move the dates in the calendar and the dates in the lab, so I might have left something missing, but for sure it's not for tomorrow, right? So don't worry, Carlos, it will be for later on. Because yes, I think that it's the one for the UML and etc. But I mean, we can leave it for after the spring break. Even if, I mean, since you have been already working on that, you will have a kind of batch uh, uh, handing hand-ins for after the spring break. But I mean, I just didn't want you to charge with with activities for the spring break, well, because the spring break is essentially meant to give you a brief, not to charge you with activities. That was the objective. Okay, right. So while other questions eventually emerge, I'm going to share my screen. So today I apologize from the beginning because I will be talking a lot. Tomorrow it will be a more participative session. Today I need to explain a little bunch of things, so it will be a lot of, it will be a talkative session, but so let's have go through this, and then afterwards tomorrow we will have a little bit more fun. So as I said, publicity, now it's about professional opportunities and other complementary information that you can have a look. That the idea is to connect you to some ideas about possible things that you can imagine regarding your professional activities. So on the left, in many different universities around the globe, in summer and in winter, there are people proposing what they call summer schools or winter schools. And the idea is that you have a week or 2 weeks sometimes where people come, and it's like with tutorials, but with a lot of hands-on activities, so that they address like trendy topics. Okay, so everything that that it's impossible to address in the university because it's emerging, etc. These summer schools provide such kind of programs, and so you meet people, etc. And there's one going on in Paris, in Université Paris-Saclay. It's about artificial intelligence. And of course, here, I'm not an artificial intelligence specialist, so I do not touch these aspects particularly in this course, because this is about engineering. But of course, you know that artificial intelligence is out there, that it's being used in many different organizations, and that it's important that you have knowledge about it. So the school is going through these aspects. It's in July, and well, like this, there are other schools, for example, again in Barcelona, in nice places where you can have fun and learn a lot. So that's one thing. And the other thing is, that's an idea about Spot by NetApp is a company, and the company is devoted to provide a solution in order to let users of clouds follow their consumption in order to optimize the economic investment that they put in the use of cloud services. So the idea is that they propose meters and or servers that are metering your requests on top of cloud services, and they show you where you might have some holes and that you might be losing money because you do not have the right subscription to this um, to the cloud, and so they propose you solutions. Okay, so these are little cartridges that observe your consumption and that recommend possible alternatives that you can use either in your practice with regards to the use of cloud services or to the type of subscription that you have, such that you optimize the economic investment that you put in the cloud. So they have a nice page with a lot of examples of use case examples, etc. So I wanted to share this with you because it's important. It's an open market, and you can consider this as an option to your professional life. Okay, so publicity is over, and now we come back to programming in Spark. Well, like if I can provide a generic picture of how to observe programming in Spark method, you can think about a toolkit. So Spark, what it provides is a set of tools that are intended to process data. And the tools are many different functions: filtering, joins, standard deviation, analytics, a lot of operations that are commonly used in order to process the data. Main difference with the MapReduce approach is that in the MapReduce approach, we have to program these operations. We have been playing with this, and here we have already built-in algorithms that implement the functions. Okay, so the idea is just to choose the right tool in order to propose a solution in order to process your data. So that's one thing. And the other thing, which is particular about this programming model, is that you have also other tools that let you exploit as much as possible and in the best way possible the execution resources that you have because you are running your programs in a cluster. Okay, which are these management operations? Is having a data collection and deciding to deploy it and fragment it across a certain number of nodes of the cluster. Another decision and another management operation that you have to do is decide whether, once the workers have produced results, whether you want to leave the results in the context of the node of that is hosting the workers, or if you want to collect the results and put them all in the space of the manager, okay, of the driver. Remember that at the very end of the lab session, what we saw is that there was a driver, there was a cluster manager, and you have the workers. And the very last exercise that we did is that we saw two alternatives. One was the workers had finished producing a result, and the result went to the file system. And that was one option. And the other option was execute a transformation called collect. And we left, well, you did some guesses, but we didn't discuss that. Collect, in fact, is bringing the partial results that lie in the nodes hosting the workers into the driver space. And so it collects everything, and then well, the program can use them for other things, or you can show them in a screen, or whatever you as a programmer want to do. Okay, so the fact of moving data across the elements of the cluster are other types of tools that we normally, when we program in a centralized manner, we do not use. They are not exhibited for us as programmers. Whereas here, these tools let us exploit this aspect. Other aspects that we can exploit through these management functions is, for example, letting some results go into cache so that other workers can have a look at the space, shared space with the cache. So this decision making is up to the programmers, and this makes you aware of the fact that you are working in this cluster architecture. Okay, so you exhibit the coordination functions that you use in order to exploit the different resources of your cluster, and you have the built-in functions that you use in order to process the data once you have made decisions on how they are going to lie within the cluster. And the whole objective of the game, sorry, sorry. And the only objective of the game is figure out how to combine the operations related to data processing with the operations related to managing the cluster, such that your program runs in the best manner possible. Okay? That's the objective of the game. Everything that I said beside this is just landing into concrete concrete arena and showing how this generic idea is implemented in a solution, and one that we use is Spark. Okay, so we bear in mind this idea. Of course, there's something that I didn't know say, and that we have to consider is that data finally are the backbone of all the operations that we are going to use as tools. Okay, so given a collection of data, we are going to decide how to fragment it into a cluster and then how to operate on it. And so we have to know the characteristics of this data. And as every data management solution, when we talk about data, we talk about a data model. And we have been discussing almost a week or two by now, is that in the case of Spark, we are going to have a generic data model called the distributed data sets, RDD. So RDD is something that you have in mind now and that you know what it is. Okay, so just to remind you what it is, it's a primary abstraction of Spark. It's a collection of distributed objects in the very general sense. I'm not talking about objects in the sense of object-oriented programming. So these are items, and items can be anything, as we said. There can be tuples, there can be documents from MongoDB, they can be anything you can, any data type that you can imagine can be seen as a collection of objects contained in an RDD. A particular thing is, as you can see here in my in the figure, it's better to say items. So you have a collection of items that initially you obtain from an ETL process, either coming from a file system, either coming from whatever persistent support you can imagine. And so you have this collection, and the particularity of this RDD is that it's fragmented across across a set of nodes. Now, it is important to bear in mind that intentionally for the system, there exists the collection as a whole, okay? Even if in reality it is fragmented across different clusters. But you and the system can reason about the whole collection, I mean the collection in its extent, okay? So without having details on who lies where, okay? So the partitions are something that you can decide as a programmer, okay? So here, the programming aspect of the functions is hidden, and it is more about a decision-making process on how to combine the tools, okay? So here, our role as programmers is more a decision-making task rather than a algorithmic programming task, okay? That's one of the main differences with respect to MapReduce. In MapReduce, we are programming algorithms that we embed in the and reduce functions. Here, these functions are already there, and now the problem is how do we build a plan, an execution plan that can run in the cluster in a parallel manner, okay, to explore parallelism. Okay, so back to the RDDs, you have this logically data collection, but in fact it is partitioned, and the partitions go to the worker nodes. And the idea is that all the nodes that will be invited to execute functions, to process the data, must have a portion of the data they need to use in their space. Okay, so that's very important, and as much you partition your data collection, the more parallelism you will have. Okay, so that's the principle. Now, when we start thinking about execution, in fact, the RDDs can be stored in the main memory of the executors, okay? So, and then, or they can lie in the local disk of the nodes. Or, I mean, if it's not lying on main memory or in the cache, okay? So when we talk, that's something that you have to bear in mind when you talk about storage. When we talk about storage, in fact, we are talking about three ways of storing the data, either on disk, either in main memory, or in cache, okay? And normally our storage solutions hide these aspects, but here we have these elements exhibited, and we have to decide where to put the data at which moment. And this is why it is important to say that the RDDs can go in either of the three spaces. And this is what allows the parallel execution. That's and other properties that we have discussed that again you have to bear in mind is this idea of the RDDs being immutable, which means that the content of an RDD cannot be modified. Okay, so what does it mean in terms of in a concrete situation? It means that when you apply an operation on top of the RDD, you will not modify the RDD, but you will create a new RDD. Okay, and another implication about this is that it requires resources. This requires resources, and this is why we are supposing that we have a cluster and that we have much more resources than as if we were working in a local machine, even if for testing we can work in these local machines. So that's the story of immutability of RDDs. And then Spark tracks the lineage information to efficiently recompute lost data. Now, what does it mean? One of the characteristics we have discussed this in previous session is that RDDs are resilient, which means that if there is a fault, we do not lose information. Okay. And do you remember which is the strategy that relational database management systems have in order to ensure durability, which is fault tolerance resistance? What is the technique adopted by relational DBMS to ensure this? You remember? Not remember? I mean, remember that in the relational DBMS, what happens if there is a fault? The guarantee is that when after the recovery process, you will retrieve the last status of the database after the last commit of a transaction. And how is it possible? Ideas? I mean, if you do not know, you might have ideas on how to do this. Are we going to stay here for a while? Please, Mauricio.
To be honest, I don't remember so much, but so durability, does it have to be about persistence, right?
Durability means that even if there are faults, what has been committed and stored will be there forever, despite faults.
Despite faults.
And how can we imagine a solution that ensures this? Imagine a system, let's say, any application. You are promising this to your users. And then how do you implement the solution so that this guarantee is possible?
Backup servers, maybe.
Okay, backup means that you do not lose data that is already stored, but what about the operations? I mean,
The operations.
imagine we are here and we do an operation, path, fault. I don't want to lose the operations that I had performed before the fault.
Yeah, it's just that I remember that the transaction has to be all or nothing, right? Because, especially because of that.
That's it. So that's the how do we say that? That's the guarantee. But how do we implement this? What we do is we are going to have a log where we annotate all the operations that have been done, all the operations within the transactions. In transaction 1, I did this, I did this, I did this. In transaction 2, that was working concurrently, happened this, this, and this. And this log, when I perform a recovery action, the system will go to the log and say, the current status of the database was the last stable status of the database was this. And now I am going to go through the log and repeat all the operations that happened before the fault in order and that were not committed on top of the data in order to find in order to find and not to lose the operations that were done before the fault. So I have like a recipe, a log, no, of what had been performed in order to within a recovery process to repeat, re-execute everything that was lost in order to not lose the operations that we have already done. So the log is critical for a relational DBMS. And of course, the log is it's like the black box, no? There are guarantees that you store frequently the log, you put it in several spaces of the disk, etc. Because if you lose the log, then you're over, right? Is this clear?
Yes, this is very clear.
Okay. Okay. So this is why I always say that the relational database management systems are one of the results of our discipline. And this is wonderful system. Can you imagine, for every guarantee, we have a lot of strategies behind that guarantee that this guarantee will be true at any case as promised. Okay, so this service level agreement provided by relational DBMS imply a lot of things to be done behind. Well, here, in order to have resilience on RDDs, this means not losing data in the presence of node faults, Spark creates a directed acyclic graph that represents the operations that have been performed within a program. Okay, so if there is a fault, it knows how to get to the last status of the data without losing information. Okay, or if the node is lost and the process must go to another node, it has all the recipe in order to be executed in order to find a consistent state. So together with the RDD, we have to think about what we call the lineage graph that represents all the operations in intention, all the operations that have been executed on top of the RDD in order to be resilient. And this is how resilience is ensured. Then RDDs, well, once you know this, we know the guarantees, we know the properties, and we know how these properties are made possible. No? Now, once we have this, what can we do with RDDs? Well, we can create RDDs, and the idea that's something that I don't remember if we saw in the lab, there was some activities that we didn't complete well. When you get the data from somewhere, from the HDFS, for example, you have to tell the system that you want this data to be parallelized. And this is how you create an RDD. Okay, so you get a set of a CSV, for example, you upload it on your program, execution program space, and then you say parallelize. And what you say what it does when you say parallelize is you create an RDD and the system distributes the partitions are distributed on the cluster, on the nodes of the cluster. And you, as a programmer, can even say how many nodes you want to intervene in order to partition your data. Okay, so that's the way you create an RDD. And this is done, of course, in a command in a programming language. Okay, so that's one of the operations that your host programming language must contain is this operation that lets you create an RDD. You remember, you do remember the notion of host programming language, do you? Do you or you don't? A host programming language is when we use relational database management systems, we have an interface with SQL, right? But we can also have a library within a programming language in order to connect to the database and perform operations, etc., because we want to write applications. The programming language that has the right library so that we can connect to the database and send queries to the database and get the results back, etc., is called a host programming language. And well, that happens in relational database management systems. That happens also, well, for example, in NoSQL systems, what it is a service, and you have the API, and any programming language can call externally the right method. Okay, so this is an important difference with regards to NoSQL systems. But in the case of the relational solutions, in the language you have this library, and well, you certainly used either ODBC or OGDC for programming your applications on top of MySQL or whatever you have used for developing applications, right? Have you? GDBC? I want to use this. GDBC or ODBC. It's for objects. For example, if you were programming in Java, you used ODBC. ODBC. Huh. Do you remember this? Right. Okay. So here it's the same. The host programming languages will have will host the operations that we use in order to communicate with Spark. Okay, and we have seen that there are many of them, and so being Scala the core programming language first used by Spark, but there are, as we have seen. So the library will contain commands in order to create our RDDs by parallelizing existing collections. Or we can also get our RDDs from HDFS, from a distributed file system, from the files stored in normal file systems or in databases, whatever that means, or by transforming an existing RDD into a new one. Okay, so these are the four manners that we can use in order to create an RDD. Okay, but in any case, we have always to create an RDD in order to start processing data using Spark. Okay, so we have the notion of RDD, we have the notion of our tools, the two groups of functions, one, the ones that process the RDDs, the ones that help us coordinate the operations and exploit the computing resources of the cluster. We have this, and now what is the Spark framework? Well, the Spark framework is the one that we install, and it manages scheduling and synchronization of jobs. Okay, so again, even if we are making decisions on how to manage the data, there are other things that have to be done with regards to the processes, and this is the responsibility of the framework. It also manages the way RDDs are split into partitions and allocates them in the right nodes of the cluster. Okay, we only say parallelize, and then behind the framework makes sure that it contacts, well, it fragments the RDD and it contacts the nodes in order to transmit the data. Okay, so that's not of our business, that's the business of the framework. Of course, it hides all the complexities of fault tolerance and slow machines. So if at some point a node is like this, it will decide to allocate our processes to other nodes so that our performance is not harmed. And again, if there is a fault within one of the nodes of the cluster, it will control this and recover from the fault without us as programmers being asked to do anything. And particularly when there is a fault, it will be in charge of rebuilding the RDDs that might get lost because of the fault of a node. So if we want to be very fancy and use the right vocabulary in order to talk about this is called recovery. Okay, so the recovery process, namely slow nodes, faulty nodes, and reconstruction of possible lost RDDs due to faults. This is done by the framework. So these are the tasks composing the recovery process, and this process is done by the framework. Okay, so we have the framework, and now we have programs, and we want to use the framework in order to run our programs. And the first component that we have to be acquainted with is the driver program. Okay, so the driver program in a Spark program contains the main method. Okay, so in any case, independently of the language, main is contained by the driver program, and it defines, in fact, the workflow of the application. In terms of Spark, what we are specifying is a workflow. Okay, a set of activities done, and in fact, it's a sequential workflow, done one after the other, that will step by step process an RDD. So that is contained, this general workflow is specified in the driver program, and it accesses one of the main things that you have in this driver program is this story of a Spark context object. In fact, this object will be the one that represents it's our entry point into the cluster. You certainly remember that we had the same setting when we configured the cluster for MongoDB. There was an element that gave us access, CLI, that gave us access to the cluster, and then we started using the query router and the fragments, etc. Okay, here you have the same notion. the program will be contained in this Spark context that will connect us to the cluster. The driver also defines the RDDs that are collected in the nodes of the cluster, and it invokes parallel operations on RDDs. Okay. So of course the workflow, every activity of the workflow is either an operation that processes and transforms an initial RDD, or it is an operation that interacts with the resources of the cluster in order to control the execution of some part of the workflow, and in order to collect, to execute other things, to share the data, to transmit the data, etc., from the different elements of the cluster. Well, it also defines local variables. The variables representing RDDs. Okay, now, of course, this seems simple, but it's not that simple, as always in computing. We are, in fact, sharing two spaces when we program in Spark. We have the local variables of the driver program, and we are dealing also with variables that in fact are distributed, okay, that represent elements, the RDDs, partitions that are distributed in the different workers. And we have to make the difference between these two types of variables, okay? So the driver program can deal with the local variables, and it can deal with the variables that represent the RDDs which are distributed across the cluster. And now, just to make sure that you bear in mind this, the Spark context object allows creating RDDs, submitting executors that execute in parallel the operations, and then performing transformations and actions. Okay, so this is the container that allows us to deal with our operations on top of the cluster. And of course, within a program, we can have this Spark context and other things happening outside that do not regard to the Spark context, and this is the right difficulty of dealing with such kind of program. Now, what happens in the? We were talking about. Do I have a figure? Not yet. Okay, it will come later. Sorry. So you have. You're going to imagine, right? So you have the driver, and you have the workers. What I have been describing is what happens in the driver. Okay, where you have your Spark context and inside your driver program. And now, what happens in the different workers of the cluster? Well, the clusters run your application using what we call executors. Okay, so you have the worker is a machine. Okay, so the machine contains some process called executor, and within the executor will host your application, your program, and it will run it. Okay. And each executor will run the operations of your application on top of the portion of RDDs that were allocated to it by the driver. So every worker has its portion of data and the program that it must execute. And it executes on this portion of data. Do I have a question?
No, sorry, I misclicked my keyboard. Sorry.
No problem. No problem. Okay. So that were yes, I have my figure. So things look like this. You have your driver program, as I said. you have here, it hosts the Spark context. And the Spark context communicates with executors, and executors have an allocated cache space, and they can perform several tasks. And executors are processes that are hosted by worker nodes. Okay, the blue ones are machines, and the yellow ones are processes. It's different from here, okay? Here we are missing the machine. So here we have a problem. And then the the data that are distributed across these workers can lie on cache, or it can lie on local file systems, on distributed file systems, or in other uh, systems, persistence support provided by, for example, the cloud. Okay. So this is how things look like in a distributed setting. Now, of course, we can have a local execution of Spark. When we are talking about a local execution, so we do not have to be surprised of the fact that we use a lot local executions for running parallel tasks. The problem when we go to a cluster is that the execution is more complex, and that if we want to debug, if we want to test, etc., having this in a cluster, it's a big burden, okay? That's one thing. And the other thing, if we are really using a cluster, normally is not dedicated to us alone. We are sharing the cluster with other people. And if we run our things that are not very stable in the cluster, this means that other users are not using the resources of the cluster, because we are monopolizing them with stupid executions, okay? So in order to avoid this, we first test and run everything locally. We see that it works right, logically speaking. And then once we are sure, then we go to a cluster setting where there we are going to test much more performance, etc. But we are sure that there are no logic problems in our solution. Okay, so that's the way it works. When Spark runs in a local setting, what happens is, let's say that we have a single PC. The whole PC will have to support all the processes and simulate the fact that we are having a cluster. So we will have pseudo workers, for example, threads that will represent our workers. And within that workers, we will have the executor, a space of cache, and a task. Okay, that's normal because you remember that any process running in any machine is always allocated with main memory, cache, and disk. And of course, this is decided by the operating system, right? So we will have our workers anyway with the same setting as if we were having different machines. Now the difference is that since we are in a single node, we, instead of having an HDFS, we have a local file system. And then here you have still a scheduler that controls the execution of your program. Okay, and as it says here, it is useful to develop and test the applications before deploying them on the cluster because of the reasons that I have described now. For example, in the first, the baby steps of the lab on Tuesday, what we did is this, but in an external machine provided by Cola, right? But it was this. The only difference, I think that we have two nodes, in fact. But anyway, it's a controlled and local setting with respect to what we have seen. Okay. And yes, please.
Yes, teacher. And what happens if the machine that has the Spark context fails?
Hey, you're over.
Oh,
Well, sorry for you. You have to you never have one driver program. In fact, in real settings, there are many masters in order to avoid this. So what will happen is that one of the workers or a new node of the cluster will take in charge the duties of the driver.
okay, I
But
see.
in a single PC, this doesn't work. Okay, I mean it fails. But in a real setting, what happens is that you have a node that takes control of the execution of the driver, and then you're clean. It continues. And well, that's something very interesting that people learn in distributed algorithms. Is one a topic in distributed algorithmic is the choice of the master, and there are many protocols that exist in order to choose a new master. There are protocols based on votes, so the different nodes of the cluster vote in order to choose a new master, or the new master, there are pools of possible masters that can take control, and so the pool is repeating everything that the master does is done by the pool of servers, such that when the master is off, the other one can take on the execution without any problems, because it's repeating everything that the first server does. So that's another strategy. So there are many different strategies like that that are studied in distributed algorithms that ensure this kind of guarantees, fault tolerance guarantees. That's a very interesting topic. But anyway, in this case, this is what happens. Beyond the fact that if you're on your single PC, we are sorry for you.
Okay, thank you, teacher.
Um, Now, it is important. So that's the general. So everything that the core elements of Spark are here. Okay. So now, what it's important is that you, in your minds, have control of the official terminology of Spark. Okay. So that you can picture everything that is happening when you are programming and when you are executing your programs. So three main aspects is the notion of executor, right? Remember that the executor is the process that hosts the execution of parallel operations performed on a portion of RDD in a worker. The notion of task, which is a unit of work that is sent to one executor. Okay? And the notion of job, which is a parallel computation consisting of multiple tasks that gets spawned in response to a Spark action. Okay, so you have the first thing that you do is um, you have your program, okay, lying in the driver, and then there are multiple tasks sent to the different workers. Okay, a task represents a line of code of your program, right? So path, it goes over the executors lying in your workers. And then there are operations that bring everything together and that conclude the execution of this little task, of this line of the program. And this is a job, okay? The set of subtasks that are executed on top of the workers in order to execute one line of your program, which represents either an action or a transformation. So, this in mind. Then, more about this. The notion of stage. Stage is very important. Each job, okay, so each big potato that is received is divided into tasks. And in the terminology of Spark, these tasks are called stages. Okay, so that's just vocabulary, but it's important because in documentation, in all the jargon of people working with Spark, they will use stage instead of task. Okay, but it's that, a task. And the output of one stage is the input of the next stage, because we are programming as a workflow, no? So the different um, activities of the workflow, well, are divided into stages, and so then you have more stages connected with each other. Well, this is true only for intermediate stages, but there are stages that produce the final results, and the final results, well, are there are no input or output. Well, there is input, but there is not a new output towards some new stages because that's the final stage. And normally what happens is that the result is either persists or within the environment of the worker or up to the driver. The shuffle operation, which exists here too, is always executing between two stages. Okay, so the interaction, the preparation of the data so that it can go from one stage to the other, this shuffling is done in order while you connect stages between each other. So they are data are grouped, partitioned with specific criteria. That's the same as we have studied in the Hadoop setting. Then there are other strategies, for example, map reducing in the sense of collecting and integrating the results of a parallel execution is done between stages. And well, of course, you have understood that since we are talking also about volume, etc. Well, it's a heavy operation, and this is done, however, by the framework. Okay, so we only know that between two stages there is something happening. We can guide the way this happens, but it's delegated to the framework. And I will stop here. So now you have the general principle, the overview of the framework, and the terminology of Spark. Another thing that we are missing, but that we will study tomorrow, is the notion of this famous DAG. Okay, so how is the process controlled, and where do we as programmers act on top of this DAG in order to make decisions on the execution of our program? So that's one thing. And the other thing is having a look at these decision-making operations to transmit the data and let the data be shared across the processes, which is an important aspect of Spark program. Okay, so that's the two things missing, and of course, well, tomorrow we will play a lot with writing programs, examples, etc., and having a look on how we play with simple things, and then how we play with the cache, etc., so that you can have a theoretical basis of Spark programming, and then afterwards in the lab we will do that, but in practice. Okay, would you have questions until here? So I honored my promise. It was a lot of blah blah. Okay. Okay, so there are no questions. I'll meet you tomorrow online, and in order to play a little bit with these notions. And meanwhile, I hope that you will have a nice Friday.